drew you a pretty circuit. We've got a battery here putting out some voltage, and we've got a resistor there, and this is just a switch. Right now it's open, and we've got an inductor. Time to go a little bit further into what inductors are all about. You see, if I close this switch, then the current will begin to flow, and a magnetic field will begin to occur inside of the inductor. The inductor itself will get pissed off that it's creating a new magnetic field, and it will try to not allow that magnetic field that it itself is creating to exist. So in order to do that, it becomes a bad battery. The inductor becomes as if it's a battery facing this direction that says, no, don't let a current go through me. And gradually, the bad battery dies. And we want to study how that bad battery dies gradually. We want to study quickly how the bad battery gradually dies. There, that's a little bit better. Now, ultimately, a current will be allowed to flow because there's some resistance here and everything kind of eases into it, and it's not a perfect inductor. But I want you to notice that the inductor is kind of like inertia in the circuit because it tends to not allow a change to occur. So this is very similar to capacitance, and I think we'll see a few ways that this ties into capacitance. But I like to think of an inductor as current inertia. So here we are. Let's get ourselves a little graph. I want to get a graph of current as a function of time if I close this switch. It's going to be doing this. It'll go from here, I should get a different color on that plot, right? This is called infrared. Yeah, I bet it's not actually infrared. And it will asymptotically approach some current here. Do you think you can figure out what that current is there? I'm going to call that I final, and I'm going to say that it probably is, well, when the bad battery is completely dead, then this will be a line, and this will be a line, and then we'll just have V and R in here, and V is IR, so this current is going to be the voltage of the battery divided by the resistance of the resistor. It will ultimately reach that. But I guess I'm interested in this time here, this characteristic time when we're up at, you know, what is it, 37%? I want to be 1 over E of, that's not on that axis right there. I'm going to call that time tau, and this is I final divided by E right here. So that's when we are most of the way up, but not quite. I haven't looked at that. I may be being a little bit sloppy on that. I'll come back and write a comment if I have. See a comment right here. All right, but there's tau, and then at 2 tau we're a little bit closer, and at 3 tau we're a little bit closer still, and we continue to get closer and closer. But this is a characteristic time for every shape that looks like this. You know the shape of this. It's a decaying exponential that's kind of flipped over, an inverse exponential, dying. And so I'm going to say that current as a function of time, this doesn't mean I times t, but current as a function of time, well, it's going to be I final times 1 minus something that's going to start at 1 and then gradually die, because, well, this looks like that flipped over. So we'll say e to the minus t over tau. And you're wondering what makes this take longer. I suppose if tau were a bigger number, then it would take longer to get up to a significant fraction. So I can draw a it taking longer kind of thing. It might be a kind of graph like that if it took longer to get near to the final current. And so, well, hopefully you've played with these equations a lot. But if you haven't, that's the kind of feel that I'm going for. So tau has to have units of time. And I'm going to define tau as, oh man, I suppose it will take longer if the inductor is better. So I think that tau has to depend linearly on the inductor, and it will take longer. Now this is maybe a little bit counterintuitive. It will take longer if there's less resistance, because the resistance eases us in to the resistance eases us into getting a current through the inductor. if there's no resistance at all here, we suddenly try to have an enormous current going through this inductor, and the inductor says no, and it takes a very long time. So it's actually inversely proportional to the resistance. So a bigger resistor ends up taking a shorter time. Really, really counterintuitive. I want to point out a little relationship. You remember when we were charging a capacitor, we said that tau was just R times C. And then we had the resistance, a larger resistor slowed down the charging of the capacitor. Turns out a larger resistor speeds up the energizing of an inductor. All right, now let's go on and investigate what sorts of things are needed here to charge an inductor. We need some voltage, and the needed voltage is the inductance times the current that we want to change divided by time. And that's just going to be this, well, the change in current is going to be I final minus 0, and the change in time is just going to be the time that it takes to charge. So this voltage that we need is the inductance times the final current divided by the time. So my plan here is to increase the current from 0 to I final in some time t, and I want to think about what kind of power is required to do that. So in order to do that, I need some power, which is current average times voltage. And so I'm going to say that the average current is 1/2 I final times the voltage, which is, well, I know what the voltage needed is. It's this business right here. So I'm going to plug that in, and I'm going to find that it's 1/2 the inductance times I square divided by the time. See, I'm plugging in this, the voltage. I'm plugging in the voltage right here, and I get that relationship right there. And this is a very interesting relationship. What if I say I'm interested not in so much the power, but what about energy used to energize, oh boy, that sounds repetitive, an inductor? Well, that's going to be the power times the time that it takes to energize it. In that case, it's going to be power times this capital T that I'm using here, all sloppy-like. And that is simply 1/2 Li square. And wait a second. If I had to use that much energy to get a current going through an inductor, because it's got some inertia, I am pushing to try to get a current to go through that sucker, then that means that that's the energy that's being stored in the conductor. And I want you to reference the energy stored in a capacitor, which is 1/2 C times V squared. Look at this for just a moment. You've got a half, right, because of some average that comes in there. And you've got the value of the thing. This is the inductance, and this is the capacitance. And you've got current, and that's the way the inductor stores energy. And here you've got voltage, and that's the way the capacitor stores energy. So there's beautiful symmetry here. So it is these guys are analogs to each other. One of them is about static and electrical energy, and the other one is about static magnetic energy. This one is about moving electrical energy, and this one is about moving, whoa, let's not even go there. But you know what I'm thinking. I know, I'm going to keep going here, I know that the inductance of a, well, what am I trying to say? Oh, the inductance of a solenoid, a simple solenoid we showed in the previous video, is mu0 times the number of turns per unit length, square, times the area times the length. We found that that was the volume also. So I'm going to plug this in right, obviously not there. I'm going to plug it in right there. And I'm going to switch colors because that's getting boring. So I'm going to say that energy in an inductor, the energy in an inductor is, wait for it, 1/2 Li square, and I'm about to plug in all this business right here. I've got 1/2, and I've got mu naught n square a l I square. Oh my goodness. But I want to point out that the magnetic field inside an inductor, well, I guess the magnetic field inside a solenoid is the result that I'm using right here, is simply mu naught times the number of turns per unit length times the current that's going through there. So I see this here. You see that I've got mu naught and n and I. In fact, I've got this square except b square over mu naught equals mu naught times n squared times I squared. You see this in there? Mu naught n squared I squared. So I'm going to put b squared mu naught to replace that. And here we go. I'm going to get 1/2 b squared over mu naught, and what do I have left? The I squared's gone, the n squared's gone, and I've got A and L. And just as we did for a capacitor, we can investigate not just the energy that's stored in an inductor, but let's look at the energy density stored in an inductor. So this is the energy in an inductor. And then lower U is going to be the energy of an inductor divided by volume because it's energy density. And if we take, what? This is volume. So if we're investigating the energy density of an inductor that has a magnetic field inside of it, and that's the way that it's storing its energy, then we find that that is 1/2 b squared over mu naught. And I want you to remember that the energy density of a capacitor is 1/2 epsilon naught E squared. So look at the similarity between these equations. Yeah, we got something about mu naught being in the denominator and epsilon naught being in the numerator, but look, we're squaring the value of the field. That's how fields store energy, as the square of the value of the field, and we're multiplying by 1/2. Dang. Yeah, one final thought. This is the energy density of any magnetic field anywhere. This result is actually completely general, so it doesn't have to be in an inductor. If there is a field that exists in space, then the energy per unit volume is that. And if there's an electric field that exists in space, the energy per volume is that. So I'm going to say that this is the energy of an electric field. And to demonstrate some of the symmetry, I'm going to show you that this is the energy of a magnetic field. Yep, see, purple, orange, great. All right, it may have occurred to you, but maybe not. I want to point out that inductors don't just have a problem getting current up to a certain level. Imagine that this has been going for a long time. You've got the voltage of the battery here, and you've got some resistance here. You've got a closed switch, and you've got an inductor. And this had been closed for long enough so that a steady current would be going through here, and the inductor becomes very happy. Now, if I open the switch, though, you can bet that starting from some initial current, which is probably, let me point out that I naught is probably going to be, well, it's as if there's no inductor here, remember? So it's just V divided by R. But the current will gradually slow down. In fact, rapidly at first, and then tapering off because there's less and less of an impetus. So this is a standard dying exponential, and I find that the current as a function of time is my initial current times e to the negative t over tau. And you saw this performance here for the rising to a certain level of current, and I realized that I got the e's mixed up. Silly. Prepping, right? That's very important. So it's at this point here that I can define tau. Let's look at it a little more carefully. When t equals tau, then the current at t equals tau is I naught times e to the negative tau over tau. And e to the negative tau over tau is simply e to the negative 1. And that means that the current at t equals tau is I naught divided by e. That's where my 1 over e is supposed to be. This current is I naught divided by E. So what I should have done up here, and I'll have it corrected in the video also, is that this is not I final over E, it's I final times 1 minus 1 over E. And 1 minus 1 over E, well, that's your favorite, right? We can put this as E over E, so it's E minus 1 over E. Really? And this is just, well, it's 1 minus 1 over E. Okay, so that's that value right there. So not only do inductors not like to start having a current, they also don't like to lose a current. So that in that way, they are extremely like electrical inertia. And frankly, I'd like to call them electrical inertia devices. It will try to not allow that magnetic field that it itself is creating to exist. So in order to do that, it becomes a bad battery. The inductor becomes as if it's a battery facing this direction that says, no, don't let a current go through me. And gradually, the bad battery dies. And we want to study how that bad battery dies. This is very similar to capacitance, and I think we'll see a few ways that this ties into capacitance. But I like to think of an inductor as current inertia. So here we are. Let's get ourselves a little graph. I want to get a graph of current as a function of time if I close this switch. It's going to be doing this. It'll go from here, I should get a different color on that plot, right? This is called infrared. Yeah, I bet it's not actually infrared. And it will asymptotically approach some current here. Do you think you can figure out what that current is there? I'm going to call that I final, and I'm going to say that it probably is, well, when the bad battery is completely dead, then this will be a line, and this will be a line, and then we'll just have V and R in here, and V is IR, so this current is going to be the voltage of the battery divided by the resistance of the resistor. It will ultimately reach that gradually. We want to study quickly how the bad battery gradually dies. There, that's a little bit better. Now, ultimately, a current will be allowed to flow because there's some resistance here and everything kind of eases into it, and it's not a perfect inductor. But I want you to notice that the inductor is kind of like inertia in the circuit because it tends to not allow a change to occur. So I drew you a pretty circuit. We've got a battery here putting out some voltage, and we've got a resistor there, and this is just a switch. Right now it's open, and we've got an inductor. Time to go a little bit further into what inductors are all about. You see, if I close this switch, then the current will begin to flow, and a magnetic field will begin to occur inside of the inductor. The inductor itself will get pissed off that it's creating a new magnetic field, and